So we're on to exponential and logarithmic functions. If you're kind of keeping track of where we are versus pre-calculus, is we're on chapter 5 at this point, which was everyone's favorite chapter, right? Yay! So just a quick reminder about properties of exponents. This 1/3 exponent, that's the same as saying the cube root of 64, which is 4 times 4 times 4, so 4. So if you have a fractional exponent, that can be a radical. Also, if you've got negatives or fractions, that's where negative exponents come in. So this could be a 4 to the negative 1 times 3, but that's not going to help us solve it. Instead, we want to distribute that exponent. We can do that since there are no addition or subtraction things going on, so you can just throw it right in there. And 4 cubed, we just said it was 64. And now you can use them in more sneaky ways, and this is what I was trying to do before, is instead of doing 2 squared and then cubing that, you could make this a 2 to the 6th and then figure out what 2 to the 6th is. It actually turns out to be 64 again. I think every answer today is 64 or 4. In this next one, once again, we can distribute that cube into that 27. I don't want to figure out what 27 to the 2/3 is. I just kind of want to leave it as is. So 27 to the negative 1, I'm sorry, not negative 1, negative 3. Can you erase there, buddy? There we go. So yeah, this 3 goes into both of those exponents and they get multiplied together. 27 to the 2/3 times a third gets us 27 squared. And now since those bases match, we can put them together. But when we put them together, we're going to add the exponents. So negative 3 plus 2 is -1, and we get 1/27 for that one. That's done. Oh, I'm recording videos all day, and I'm really running out of brain power. I almost broke for the day, but I was like, nah, I'm going to keep going. So what we want to do is we want to rewrite this one to have a base of 3. So instead of a 9 there, we want to try to make it a 3. So we want to say, okay, 9, you are 3 to the what? Hint, hint, this is kind of what logarithms do. Well, 9 could be 3 squared. So this 9 to the 2x, we're going to make it a 3 squared instead of that 9. Can I actually have a 3 there, please? And then we got 2x. We want to multiply those exponents together so we get 3 to the 4x. Huzzah! We did it. Wait. All right, now a little bit more about exponentials. So exponentials, there's 2 types. There's exponential growth and exponential decay. If our b value is bigger than 1, we're going to have a lot of growth because 0, 1, 2, 3, it grows faster and faster. So we start out with 2, and then it's 4, and then it's 8, and then it's 16. So each step we grow even faster than we did before. If you want to look at decay, that's when you have a number that is smaller than 1, but bigger than 0, because we can't use negatives for our base. Yeah, we can't use negative for our base. So this one, it's slowing down how quickly it changes. So if we go again, 0, I keep saying 0, but I don't even use it. So 1/2 to the first is just 1/2. So if you square that, it becomes 1/4, so it becomes smaller, but not quite as small. And then it's becoming 1/8, so it's shrinking, but the rate at which it's shrinking is decreasing. Our general form, we've got B, this is our growth, B is our growth rate, A is considered the initial value, and then K, I think, is like the starting point, something like that. Some stuff about the domain in general for exponentials. So this is just a regular old b to the x, nothing fancy going on. Our domain is going to be 0 to infinity. It's not going to be 0 to infinity. It's going to be -infinity to infinity. All real numbers work. Our range is going to be 0 to infinity. Our x-intercept is going to be none. It will never touch the x-axis. It does have a y-intercept, and that y-intercept is going to be 1 unless it's being changed by moving up and down. So you want to imagine if you put b to the 0, that's just 1. So that's what our y value is going to be. Our horizontal asymptote is going to just start at x equals 0. So it's a y equals 0. I really need to quit for the day. I think this is going to be my last video for today. Cannot say anything right. Y equals 0 because it's a horizontal line, y equals some number. It's never going to cross that x-axis. That's an S. All right. So if we wanted to look at this one and we wanted to graph it, we could make a rough graph of it. We know that it normally looks like this. Whoop. That's our normal exponential growth graph. I know it's growth because 2 is bigger than 1. It's going to move up 3 though, so I want to take that graph and I want to pull it up some. Hi, it's Future Ron Jack. I just finished doing the video and I was complaining about how I needed a break. Well, I went back through it and yeah, I made a mistake. I did this one wrong. So I've edited it out and so now I'm going to do it correctly. The transformations, there's a particular order that you need to take care of them for graphing this function. So in order to graph it, there are 2 transformations. It's flipping over the x-axis and it's moving up 3. And it's important that it's done in that order. In the one that I cut out, I did the up 3 and then flip. That did not produce the correct function. You kind of want to think of like order of operations. Multiplication, that multiply by negative, is something that's going to happen first, and then you add and subtract. So it's going to flip and then move up. So its graph should look like, whoop, whoop. So normally it would be right here. There's our normal exponential growth graph, but that thing is going to flip immediately to do its transformation. So let me flip it, bam. Oh, but it changed where my x-axis was. So it's going to flip over the x-axis, and then it's going to move up 3. So 1 to get to the axis, 2, and then 3. So then its asymptote is actually going to be above it at, so it's going to flip 0, 1, 2, and so it's going to have an asymptote at 3, right above it. So line y equals 3. So it has this point right here at 0, 2. And it also has one more point, which is like when you plug in 1 for its exponent, it has 1, what? 1, 1. Sorry. Again, I need a break for the day. This is all I can do. All right, so our domain is all real numbers because we've got no issues going along. Our range is going to be from highest it can go is 3, and it's going way lower than that. So way lower than that, and the highest it can possibly try to reach to is 3, but it's never going to quite touch it. Since it can never quite touch it, it stops right there. It has no x-intercept. It does have that y-intercept that I already wrote down. And that is at 2. Finished. Okay, hopefully that's correct now. Back to past Ron Jack. If you'd like to see an additional one, I do this one. It's a graph of e to the x plus 2, same idea, just kind of bumps up a little bit. E is an important thing for exponentials. It's a number about growth. It has a lot of interesting properties in terms of exponential growth and exponential decay. That's why it usually pops up in the exponentials chapter. We can use these tricks of graphing in order to even solve ones if we want to be extra fancy. So if we go on to Desmos, I just do Desmos in these videos because it's just faster. So if I graph y equals e to the x, e to the power of x, please. There, I've got my nice exponential growth graph. If I could solve it by graphing another line, y equals 4, and so now that I've got two y values, where these two y's end up meeting, that's going to be the solution of e to the x equals 4. So, boop, right there. So our x value of 1.386 is going to be our solution for that one. Nice and fast, just finding the intercept. So we've got a word problem here now. We're going to use that general form that y equals a times b to the x plus h. So our growth rate is increasing at a rate of 3.75 per year. So we want to take that percent, we want to turn it into a decimal. So 0.375. Now, if I just use 0.375, that's less than 1. We want it to be growing, not decreasing. So we're going to add 1 to that so that it's a number bigger than 1. So it's going to have the population it already had and the additional new people that are growing. So we're going to do 1.0375 to the x. The initial population is 500,000, so we're going to do 500,000. For our initial population, and that equals y. Now we want to figure out when this thing is going to reach 1 million. You know what we're going to do? We're going to do the same thing we did up here. We'll make a new Desmos tab. So we've got y equals 1,000. There's a million. And we got y equals 500,000 times 1.0375 power of x. I'm going to have to zoom out a bunch so I can actually see this thing. See, there it is, but it's way up here. There we go. So we need to figure out where these two meet. And it looks like it's going to take 18 years in order for the two things to meet up. Because, yeah, that's where they're meeting. And it's great. So 18.828 years. Woohoo! Next, we got logarithms. So logarithms are the inverse of exponentials. So they're really just the reverse. So 3 to the what is going to be 243. That's what a logarithm is trying to do. And it has very similar properties to how exponentials work, but they're all reversed because that's how inverses work. So its domain is limited, just like the range of an exponential was, 0 to infinity, but its range is got free form. It can go nuts, all real numbers. It has an x-intercept. It is at, no wait, yeah, it does have an x-intercept. It's usually at 1. And it's got a y-intercept at none, because the other one had a y-intercept. It's never touching the y-axis. It just kind of like shoots off like that. It has a vertical asymptote right here on the x-axis, which is a vertical line, x equals 0, just where x is 0. It never quite reaches that. If you'd wanted to, like, you could do the same thing that we did with exponentials, but like doing that shifting around of like moving it to the left and then up 1 and then flipping it. It does get like a stretch going on here too, since it's got that 3, but it's not really worth it. It is interesting when we talk about it in terms of trig functions, but it's not quite interesting when we talk about it in terms of logarithms. You can't really notice the difference, so I won't bother. I will, however, show you how these two things are inverses of each other. So we're going to do that Fogg and Goff thing that we were doing earlier to prove that they're inverses. They should both spit out x when we shove them into each other. So here we go. Let's try it. Let's start with Fogg. So f is e to the 2x, but instead of x, we're going to do the ln of the square root of x. So goofy thing about logarithms that you may or may not remember is that you're able to take out exponents that are inside of them, ln of x to the 1/2. So we can take that 1/2 and we can pull it in front of the logarithm. So we end up with e to the 2 times 1/2 and then an ln of x. 2 times 1/2 is just a half, or it's just 1, and we end up with ln of x. Now, e to the ln is an operation that is undoing each other, just like squaring and square rooting. E to a log, its base is logarithm, ln, undoes itself. So that e and the ln are just gone, and all we're left with is whatever was inside of the logarithm, in this case, x. Makes a little more sense when we do it the other way, which we're about to do. Goff. So we've got the ln, the square root of e to the 2x. So if we've got e to the 2x, that is really the natural log square root of e to the x squared. And if you square square root, you've really done nothing. So that's just gone. ln of e to the x. Just like what we were saying before, where if you've got an exponent inside of a logarithm, you're able to pull that in front. We get an ln of e. And here's a place where you can do that translation rule. So we're trying to figure out what the ln of e is. I'm going to do that over here. So the ln of e equals what? So you could translate that as e to the what is e, because we've got a base of e. So e to the what is e? Well, e to the 1. So that is just 1 times x. So that's just x. Since we did Fogg and Goff, and both of those compositions produced x, that means that these two are inverses of each other. We've got some nice inverse functions. And I think that's it. I think that's it for today. Yeah. So here is the TLDR version again. We mostly talked about graphing these things. We're going to talk more about solving them a little bit more next time. I've also kind of condensed and probably written better or more accurately how to graph these functions, especially their interesting point, making sure you graph 1 and the base for when you're graphing an exponential, and base and 1 when you're graphing a logarithm. It makes it a little bit like you care about the intercepts and you care about that point. That's about all. So that's it for kind of our introductions to exponentials and logarithms. Next time, we're going to do some more solving as well as some more properties with logs. Thanks. Bye-bye. I'm going to take a break for today.